Hello everyone and welcome to Instant Biology by Dr. Nilab. The topic that we would be dealing with today is fluids in motion, and that is a part of bioprocess engineering lecture series that we have already started. This lecture would be on fluids in motion. We had talked little bit about the fluid flow in one of the lectures of my bioprocess engineering series, but this would be specifically upon the concept of streamlined flow or laminar flow, and also we would be discussing about turbulent flow. Apart from this, we would also be dealing with the concept of shear stress. Okay, so now let us start what is streamlined or laminar flow. Before going into the streamlined concept or laminar flow concept, I want you to understand that this streamlined comes from the term streamlines. Okay, what does streamlines mean? So streamlines simply means that it is a method through which you represent the variation in velocity. Okay, so suppose, let me show you that suppose this fluid is flowing in this direction. Okay, and what you can see, what you can observe if you look closely is that I've tried to keep the distance between all of these lines equal. In this particular diagram, in the first diagram, I've tried to make the distance between these lines is equal. Okay, that is why I have written equidistant lines. So whenever a fluid is shown, a motion of the fluid is shown in such a way that it is represented by equidistant lines, then it is considered that the flow is moving, or the liquid is moving, or the fluid, not exactly liquid we are talking about the fluids, and fluids comprises of both liquids and gases. So when we are talking about equidistant lines, then this clearly means that the fluid is moving with a constant velocity. Okay, constant velocity, it is moving with a constant velocity. But the concept or the understanding changes. Look at this. Suppose what I've kept, I have placed a ball in the direction of the fluid. Suppose the fluid is moving in this direction and I have placed a ball inside that fluid. What will happen? Some fluid would move over the ball, some of it would move under the ball, right? So this is how it's looking like. So this is a ball and this was the direction of the fluid, and you can see that over here the lines are equidistant. I've tried to at least make them. If you do not, if it does not seem, try and understand that these lines are equidistant. Over here in this region the lines are equidistant, but as they cross the ball you can see that the distance between these two lines and these two lines has decreased. Okay, so because the distance has changed, because the distance has decreased, whenever, or let us understand this in this way, that whenever the distance between these two lines would be decreasing, it simply means that, or the spacing between these two lines is decreasing, it simply means that the variation is seen in velocity. Previously it was equidistant, that means the velocity was same, but over here these layers would be having a higher velocity. Since these lines have decreased, since the spacing has decreased, we want to show over here that variation in the velocity is existing. These layers, or if the distance is lesser, we say that the velocity has increased. Okay, so this is the condition. This is what we mean by streamlines. This is just a way to represent the flow of the fluid. Okay, what I want to tell you in the next portion is that these lines, these streamlines are telling us, are giving us the information about the net effect of the fluid motion. Net effect. When I say net effect, I simply mean that individual particles that would be moving in these lines may be moving in an erratic fashion. Okay, so the net effect is that they are moving in this direction, but the individual particles that are present in this lane, or in this plane, or in this plane, they are moving in erratic directions. So individual, that is why I've written over here that individual particles may be moving in an erratic fashion, and this actually shows that only the net effect of the fluid motion is being shown with this diagram. Okay, now understand that slower is the rate, or slower is the flow rate, or slower is the velocity of this fluid, more it would be resembling, or more it would be representing the streamlined flow, right? So by streamlines we have said that they are equidistant, we understood this much, but this actually will remain the case only when the fluid is having a very less velocity, it is moving at a very slow pace, then only this streamlined nature can exist. Otherwise it would be far from the streamlined motion. Okay, I believe you would have understood this. So that is why I have written over here that slower is the flow, more it represents the actual motion. So the slower is the flow rate, we call it as streamlined or laminar flow. So the liquids or the or anything that is flowing at a very slow rate, you call it as a streamlined motion or a laminar flow, right? But let us consider that the flow rate is very fast. Okay, the velocity with which the fluid is moving, it is very fast. If that is the case, then what will happen? The particles that are present over here, they would be more erratic, okay, and they would cross each other's way. These are the streamlines. The particles that are present in these streamlines would cross with the particles that are present over here. These would cross over with this would cross over with this. So there would be complete jumbling over, and the particles would crisscross each other. So this is called as turbulent flow. Okay, this is called as turbulent flow when this kind of flow is existing. How can you convert a streamlined flow into a turbulent flow? Just increase the velocity and the erratic motion would begin, and the streamlined would be converted into turbulent flow. Now this turbulent flow results in a kind of a specific phenomena that are called as eddies. Okay, so let me explain it to you with the help of a diagram or with the help of a concept. Now suppose the liquid or the water is flowing in this particular direction. Suppose suppose a stream is flowing, stream of water is flowing, and what I do is I place my hand in front of that stream. Okay, so the stream is moving in this direction, I place my hand against this stream. What will happen? You will see eddies over here. What does this eddies mean? So you will just see something like this. Let me just show it to you. That suppose this is the direction of the fluid and I keep something just opposite to this. What will happen? These liquids will strike over here and they will show circular motion over here. Okay, so a little or a small portion would be seen over here, which would be showing very localized region. It would be present over here that would be showing circular motion. That is what is called as eddies. So local regions of fluid rotation are called as eddies. So this is a representation of turbulent flow. If you see I mean to say, if you see the phenomena of eddies, then you can be sure that actually a turbulent flow is existing in that particular fluid. Okay, and how does this occur? I have shown you an example also, that this is the actual way in which the turbulent flow or the eddies are formed. So having understood the concept of turbulent flow and laminar flow or streamlined flow, let us move on towards the concept of shear stress. So what is shear stress? Let us understand this. Let me just give you an example with the stack of books. Suppose I have multiple books, book number A, book number B, C and D. Okay, so there are 4 books. What I'm doing is I am just applying a force in this direction. I'm applying a force in this direction. What will happen? What will happen? So this particular book, the book that is present on the top, will show a velocity of, let us say, v1. The book at the just lower level to A would show a velocity of v2. This will show a velocity of v3, and this will show a velocity of v4. Now, why is it so that all the velocities are different? Why wouldn't all of them show a same velocity? That is just because you see, the book that is present at the top does not have anything above it, so it is not experiencing any mass above it, so it would be displaced at a higher distance, or it would be displaying a higher velocity through which it will move. Next comes the B, it will move at a lower velocity. C, because it has the mass of A and B above it, it will move at a lower velocity than B, because B just had A above it, so the velocity was little lower than V1. V1 is highest, V2 is little lower than V1. V3 would be lower than V2 because A and B are present on top of the C. And finally, above D there is A, B and C, which would be moving with a velocity of v4, that is the least. Okay, so this is the concept. This can be understood very well. Okay, so this shear stress basically can be understood with this concept. Now it develops when different parts or layers of the fluid move relative to each other. Suppose these two are fluids, okay, they are moving relative to each other, they are in contact, they are moving relative to each other. And this kind of shear stress develops only when they are in contact and moving with respect to each other. Different parts are moving with relation to each other. Now what happens is the interchange of molecules between the layers would take place. Now let us understand this A, B, C and D are not the books, they are the fluids. What will happen, since they are in contact with each other, what will happen? The layer that would be facing the highest velocity and the layer that would be facing would be having a little lesser velocity, what will happen? There would be an exchange of the molecules between, or particles between them. That means the higher velocity particles from layer A would come towards layer B, and lower velocity particles of layer B would move towards layer A. And the resultant would be that the higher velocity would be lowered down and the lower velocity would be increased. So this can also be understood with the help of transfer of momentum. Okay, so because this is moving, this top layer is moving and this bottom layer is also moving, but the momentum, because mass into velocity is equals to momentum, right? So because the momentum of layer 1 is higher, it would be transferring a little bit of momentum to the second layer. So this is what I'm saying, that interchange of molecules between the layers would take place, and this would result in the drag, viscous drag or viscous forces. Now if this layer is moving at a faster rate and the lower layer is pulling it back, so what is this called? This is called as dragging. Suppose you want to move forward and your friend is pulling your leg from the back. So this is called as dragging backwards, right? So this would be called as viscous drag, and this would result in viscous forces. Okay, so this viscous drag would result in viscous forces, and as I have explained you that the momentum would be transferred between the layers. Now what can be a mathematical formula for shear stress? How can we explain it with the formula? It can be simply explained with the help of force by area that is in contact. Okay, so the force that is being applied and the area that is in contact. So this area is in contact, I mean to say the two layers that are in contact, that area. So force upon area is the shear stress. Okay, now I mean to say you would be knowing what the unit of force per unit area is. Okay, so you should always remember, I would again say that you should be always remembering about the units of whatever things or whatever parameters you are studying. So force per unit area over here would be Pascal. Okay, so the unit would be Pascal. It's one of the units. So gases, in case of gases, what will happen is that because gases, in case of gases, what happens is the molecules are far apart. Okay, the molecules are far apart, so they are not in very much contact with each other. So molecular exchange would only result in the dragging of gases backward. So gases and liquid essentially have one difference, that the molecules are far apart in case of gases, but in case of liquids the molecules are pretty much close to each other. So gases have only, or they can drag, the layers of the gases can drag only when, because of the molecules traveling forward and backward between the layers. But in case of liquids, the liquids are closely in contact with each other. So apart from the particles that are moving backward and forward, there are cohesive forces also. Now suppose if I give you the example of water. So water molecules are attracted towards each other with the help of cohesive or attractive forces that exist between the water molecules, right? So this is about the cohesive forces. Next, in turbulent flow, what happens? I just want to explain you the turbulent flow in light of shear stress. Understand this. This is a very important concept and you would enjoy it. So whenever I gave you the example that this is the liquid that is flowing and I have put my hand against it, so this liquid will strike over here and the eddies would form over here. What will happen? The velocity of the liquid is suddenly changing from very high to very low. I believe you would be understanding my point. So this V1 would be decreasing to a very higher extent in a very short span of time as well as distance. I believe you would be able to understand what I'm trying to say. So this is a very, very small distance in which this is happening, and the velocity is suddenly decreasing from very high to very low. Now this is causing a large and abrupt change in velocity. This would result in the turbulent flow. This is why you can see the turbulent flow, a large momentum exchange can be seen, and this is why this turbulence or eddies are formed. So when does it becomes a very essential point that how can you judge that whether a fluid is moving in a streamlined flow or it is moving in the let us say about turbulent motion. Why do you think, or how would you suggest that this fluid is moving in a streamlined motion, or is it moving in a turbulent motion? How would you judge that? So the best way to judge it, you cannot you cannot assess that through your eyes. The best way to judge that is the Reynolds number. Okay, so we would be talking about Reynolds number in the next lecture, and we would also solve some examples, some questions that have already come in the GATE examinations on the Reynolds number. Okay, so this brings us to the end of the concept of turbulent and the streamlined flow. So I have a very important announcement to make, that GAT-B batches would be starting from January, anywhere in the January. I have still not decided the dates, but yes, GAT-B batches would be starting in January. So the students who are interested to join us for those batches, kindly message me on Telegram, or you can comment on the description of this channel. Apart from this, the Introduction to Bioinformatics courses and Computer-Aided Drug Designing courses are also coming to their second the second batch has started of December. So if at all you want to enroll yourself for the Computer-Aided Drug Designing or Introduction to Bioinformatics courses, you can again message me on the Telegram, as well as you can comment on the YouTube channel description, the comment box. So I would be more than happy to help you. Thank you so much. Have a good day.